Okay, so hopefully you can see my screen. If you can't, let me know. So I will make the last presentation as a participant. And so I will try to avoid repeating some of what has already been said in the previous three presentations. And I'll try to focus as much as possible on the mission design that we adopted in our part of this training. So in my case, I was in a team with Elmin Softic from Bosnia and Herzegovina. So I'll present a little bit about our design that we developed during the HeptaSat training. So I'll talk about, I'll divide my presentation into three main parts. So first of all, a little bit about me and my research, and then my CLTP experience, and then I'll conclude by talking about what I hope to do based on the knowledge I've gained in this program. So first of all, a little bit about me. So I was born in France, but I'm also half British, and I spent my bachelor life in the UK. So I went to Durham University. Some of you may have seen Harry Potter movies, and in fact, part of the movies were filmed in Durham Cathedral, which is maybe the most famous monument in Durham. At that time, I also spent 1 year in Hong Kong on exchange, where I studied mechanical engineering. And after that, I came to Japan. So I did a master's in space engineering in University of Tokyo, and then a PhD in the same place. And I also spent 2 months at QTech, so in the south of Japan, during my PhD, where I had the chance to work on small satellites with people from around the world, including EOS. So that was a really fantastic experience. And then it seems I liked Japan a lot because I'm still there now working as an assistant professor also at University of Tokyo. So I have two main research interests. The first is, and these are kind of relevant to why I wanted to join CLTP. So the first research interest is small satellite mission design. So I'm interested, for example, in how we can use small satellites for deep space exploration. So this is a mission design I made with some colleagues for Enceladus Explorer, so one of the moons of Saturn. This is another mission I designed for Earth observation using solar sails. In addition, I recently worked on a project with satellite formation flying, so multiple satellites kind of operating together by adjusting their orbits for scientific observation of Earth aurora. And then finally, I've also had the chance to work with a university in Cambodia to develop a joint CubeSat project with them. So for me, part of the one of the things I enjoy the most about space is the opportunity to work together in teams with many people from all around the world. So this is why I'm so excited about working in space field. And then my second research interest is a little bit different. So it's more about space history and policy. And in particular, I'm very interested in how space can provide a method for collaboration between different countries. So for example, I've done some research on the history of country-first satellites and how international collaboration is involved in that process. I'm also interested in how countries collaborate on a regional basis. So I've done some research on regional space agencies and the history of space in Southeast Asia. And I'm also interested in how countries collaborate to develop specific technologies, and in particular, solar sails and different types of space sails. So these are some of my main research areas. So I wanted to join CLTP in order to go a little bit beyond my focus only on mission concepts, more towards the hands-on practical side. And as I'll explain later, this is something I was able to do in CLTP. So for me, my CLTP experience, I would say, can be summarized in 2 words: challenge and understanding. So I'll explain why I chose these words in the next few slides. So in terms of the mission that Elmin and I designed in this CLTP, we decided to focus on a re-entry mission. So in other words, what happens to satellites when they come back into the atmosphere. So I'll explain a little bit about the background of this mission, and then I'll talk about our design during CLTP. So first of all, in terms of background, you may have seen recently SpaceX. So SpaceX successfully retrieved a rocket that landed back on the launch pad, which was very impressive. So for rockets, we're kind of maturing the technology, but for satellites, it's still very difficult to return a satellite into space. So basically, after we launch a satellite, it will just either stay in space or it will burn in the atmosphere after the end of its mission. So this is one of the biggest challenges for satellites. So maybe we can summarize it like this. So it's quite easy to get it up, but it's very difficult to get it back. And in order to kind of improve our ability to do this, we need more information on satellites' aerodynamics. So in other words, how satellites interact with the atmosphere. So this is going to be important. It's already important for activities like debris removal and in-orbit servicing. And in future, it will become even more important when we think about entry, descent, and landing, and when we think about exchanging payloads and cargo between different planets in the solar system. So this is one example of a project I worked on in the past where some of the dynamics of the satellites could not really be explained based on available knowledge on aerodynamics. So these points show us that we need more information basically on how satellites interact with the atmosphere. So this is a video that shows advertising, but I will skip this. So basically this video shows the dynamics of the Artemis 1 capsule when it re-entered the atmosphere after its initial mission. And you can see that during the re-entry process, it heats up and there's quite fast oscillation in the atmosphere. So this was the first atmospheric entry pass to reduce the energy. And then finally, it will make another atmospheric entry pass. And in this case, it will finally enter the atmosphere. So you can see the oscillation of the spacecraft is getting faster and faster as it enters more dense atmosphere. You can see it begins to heat up. And then finally, it begins to fall. So you can see we move from space into the atmosphere. So the color of the sun changes. We can now see the sky. We're in the atmosphere. Parachutes are deployed. And then finally, at the end of this process, we hit the ocean and we have splashed down and the mission is finished. So for these type of very large capsules, it's quite easy to control the orbit during re-entry because we have a very large spacecraft with propulsion. But for small satellites, it's much more challenging. And so what we wanted to do, Almin and I, in our CLTP mission was to propose a method of increasing our knowledge of the atmosphere. So this is basically the concept of operations of our proposed mission. So our idea is to launch a satellite, a 2U CubeSat, so very small, into space, and deploy it from the International Space Station. So firstly, we detumble it, so we stabilize the attitude. It becomes so that it points into kind of a fixed direction. And then we release a small satellite from within our main satellite. We perform some experiments, and then at the end of the life of the satellite, it is brought back into the atmosphere and it burns up. And in this process, we want to achieve three things, basically. So first of all, we want to kind of visualize using a camera how the small satellite is going to move around, how it's affected by aerodynamics. We also want to successfully, from a mechanical perspective, we want to successfully deploy the satellite using a tether. And finally, from a scientific perspective, we also want to gain information on the atmosphere using this satellite. So these are some of the experimental results that we obtained during CLTP. So you can see here that we were able to establish communications between our two small satellites. So we emulated a ground station. So this kind of simulates the ground segment that would be communicating with the satellite in space. And we also measure the signal using an oscilloscope and using a terminal on our computer. So this was a really nice chance for me to gain access to this hardware side and software side of space missions that I had not really touched upon before. This is another interesting result. So we tested the GPS sensor for our mission, and you can see here that we were able to walk around the campus near the training center to confirm that our GPS system was working correctly. And then finally, this is the kind of hardware that we developed. So we were able to integrate motors and release mechanisms into part of the satellite so that this one would be deployed. So reflection, so these two words, challenge and understanding. So from viewpoint of challenge, we learned that it's important to budget time very effectively during spacecraft missions. So typically things will not always go as planned. So it's important to have some kind of buffer time or contingency time as part of the mission design process. It was also very interesting to see that integrating a complete CubeSat is actually quite challenging. So experiencing that challenge was a very nice opportunity. And then, as some of the previous presenters also mentioned, it was a very intense schedule. So that was also quite challenging. And finally, in terms of understanding, so this CLTP was a really fantastic chance to speak with people from all around the world, including Japanese TAs. So learning about different approaches for space engineering was very rewarding. And finally, beyond the technical stuff, we also had the chance to make new friendships. So that was a very valuable experience. So in future, I'd like to transfer this knowledge to new generations of students in Japan and overseas, and hopefully incorporate some of what I learned into my own projects. So I'm interested in how people collaborate in space projects. So hopefully what I learned in CLTP can also be helpful for that. So thank you very much. And if you have any questions, I would be very happy to respond to them. Thank you.